So we are ready here to take a look at one of the more challenging concepts that we're going to be doing in this class. So this concept is key as we move forward. We're trying to make sure that we understand the idea that our sample mean and our sample standard deviation are variables. And so what I want us to think about that for a second. If we have a population that's defined, so we know exactly who our population is, and we find the mean for that population, that mean is a fixed quantity. It doesn't change. Okay, so if I look at, maybe I look at a group of 25 adults and I measure their heights in inches and I calculate the population mean for that group, that population mean is fixed. It's not going to change. But what I want us to think about is, what if we instead just took a sample? So what if we didn't ask everyone in our population, but we just took a sample, so a subset from that population, and we calculated the mean? Well, depending on which particular members of our population were included in the sample, we would get a slightly different sample mean. And so the idea here is that the sample mean itself is a variable, and it's gonna vary depending on our sample. And so what we're going to do is we are going to look at an example, an overly simplified example, where we have a very tiny population size. So normally a population is large, but we're going to look at a small population of 5 dogs. And so our population size n is 5. And we're going to look at the variable of interest, which is the leaping distance in feet that each dog leaps off of a dock. And so we're measuring the dog's leaping distance for this population of 5 dogs. Okay, so because we happen to know all 5, we could actually calculate the population mean. So I'm going to do that over here. The population mean notation, remember, is mu. And the way we find the mean is we add those all up and divide by how many there are. So we've got 15.2 plus 19.5 plus 21.3 plus 14.6 plus 17.9. And that gave us 88.5. There were 5 dogs, so we divide that by 5, and we get 17.7, and those are feet. Okay, so we actually know the population mean in this case. Normally, we have a large population. We don't know the true population mean, and we're trying to estimate it by taking the sample mean x bar. So we would take some of these individual dogs, find their sample mean, and use it to estimate that population mean. So what I was trying to do here is save us a lot of time. So I gave us basically a table here where I have what's called the sampling distribution of the sample mean for samples of size 2. So what I did is I said, okay, imagine here's our population of size 5. What if we took a sample of only 2 dogs and used that sample of 2 dogs to try and estimate the true population mean? So what I've done is, to make it a distribution, we have to have every possible value. So I have every possible combination of 2 dogs from those 5 dogs. I have those corresponding leaping distances for those 2 dogs. And then I have the sample mean that would have resulted. So for example, if I happen to get Max and Drake as the 2 dogs in my sample, those leaping distances were 15.2 and 19.5. And if I add those together and divide by 2, I would get a sample mean of 17.35. And so I've done that here for all of the possible samples of size 2. Ordinarily, we would take one possible sample of a given sample size, and we would hope it was a good estimate of our population mean. What I've done, though, is because, again, I took a very small population size and then took every possible sample of size 2, is what I want you to see is then if I take all of these possible sample means and I add them all up, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So if I add all those up, so the sum of those x bars, and then I divide by 10, what I end up getting is 17.7. You'll notice that was actually the true population mean. So that's an important thing to recognize about the sample mean. It tells us that it is an unbiased estimator of the population mean. So for any given sample of size 2, you'll notice none of these are right exactly at 17.7. So none of them are perfect. Some of them are closer than others, okay? But again, if we add all those up and divide by how many there were, we got the same as the population mean. So doing this again, so I continued the process. This time I did it for all samples of size 3. So lowercase n is 3 this time. Lowercase n was 2 up here, right? So if I looked at every possible sample of size 3, now I have a little bit more data. So I have more data from the population being included in the sample. What I hope you would expect to see there is our sample means would be all, on average, a little bit closer to that true population mean. So when I took 3 dogs at a time and calculated the sample mean for each one, so here, for example, I took 15.2 plus 19.5 plus 21.3 divided by 3, and I got this 18.66 repeating, okay? I did that for every possible sample of size 3. And again, if I add all those up, there happen to be 10 again. If I add up all those possible sample means and divide by how many there were, I get 17.7 again. So you'll see that trend there. We're gonna do this one more time. So here we've gone ahead and we've looked now at samples of size 4. Remember, my whole population was only 5 dogs, so this is the biggest possible sample size I could get. I'm taking 4 out of the 5 dogs for my sample, calculating the resulting sample means. This time there are only 5 of them, but if I take the sum of those sample means and divide by how many of them there were, I again get 17.7. So what I'm wanting you to notice here is that for all of the possible sample sizes, the mean of all possible sample means ended up being equal to the population mean. And so notation-wise, it looks like this. So we're saying the population mean of every possible sample mean is the same as if I just knew the population mean to start with. Okay, so that is, I put a couple stars by that. That's going to be something that we need throughout the rest of the semester. Okay, and then the next thing that we need to talk about is the variability or the spread of those means. So if you notice back over here, right, back when we looked at samples of size 2, my smallest sample mean was right here, right? If I happen to get the dogs with the 2 shortest leaping distances, I would get the smallest sample mean of 14.9. If I happen to get the 2 dogs with the longest leaping distances, I'd get the biggest possible sample mean right here, which is 20.4. And you'll notice there's about a 6 point or a 6 foot, right? These are in feet, leaping distances, a 6 foot difference there. So that's fairly substantial. As I move down here and I look at samples of size 3, now my smallest possible sample mean is 15.9, and my largest possible sample mean is 19.56 repeating. So you'll notice now I've cut that spread down to about 4 feet, right? There's less variability among those sample means. And then as I get to samples of size 4, my smallest possible sample mean was here at 16.8, and my largest was here at 18.475. So we only have this time not even 2 feet of difference in our variability of those sample means, okay? So this can be seen in the dot plot that I did down below here. I did a stacked dot plot for us. And so what I want you to see here is that if I look at, so I've got a scale here. This is just representing leaping distance in feet. And we're going from 14 to 22. And each of these are the original 5 observations. So this is the first dog, the second dog, the third, the fourth, and the fifth. And those are their individual leaping distances. So those are X's, they're not means yet. Once I took samples for every possible sample of size 2 and calculated the sample mean. So you'll notice if I add these two together and divide by 2, I would have gotten this as my sample mean, right? So that was that lowest sample mean for samples of size 2 at 14.9. Okay, and we do that for each possible combination here, and these were the possible sample means for samples of size 2. You'll notice as my sample size increases, what happens with the spread of those possible sample means is it decreases. So as my sample size increases, the spread of my possible sample means decreases, right? So by the time I had samples of size 4, I had a lot less spread in what my possible sample means could be than when I only took samples of size 2. So what that should indicate to you is that the bigger the sample size we can take, the better, right? As I increase my sample size, I'll have less variability in my estimator of the true population mean. Okay, we are going to see this appear in a formula in just a second. So what that's going to show us is here you'll see that as our, here we go, as our sample size increases, that gives us a larger and larger denominator, and so the spread of the possible sample means will decrease. Okay, and so what we're saying is that the spread of all possible sample means is going to be found by taking the original variable's standard deviation and dividing by the square root of the sample size. That again is a very important formula that we're going to use a lot throughout the semester. Okay, and so what this brings us to is something called the central limit theorem for sample means. This is a really big one in statistics, and it allows us to do lots of the statistical tests that we do. And what this tells us is if X is a random variable with a mean mu and standard deviation sigma, X may be normally distributed, it may not be, so that's important. We don't necessarily need it to be normally distributed. The central limit theorem tells us that for large enough sample sizes, so as my sample size n gets bigger and bigger, that this random variable x bar will still be approximately normally distributed no matter how the original variable x was distributed. And so usually this large enough number is about 30 or more. So we're saying, we're not saying that x magically becomes normally distributed, but we're saying the distribution of all possible sample means x bar becomes approximately normally distributed with mean mu, and that's from right here, and standard deviation sigma over the square root of n, which was right here. And so I'm going to show you this in a picture. I think it's easier to see. And so I'm going to start us off with a variable x that is not normally distributed. So I'm going to draw a histogram, and I'm going to draw a histogram. We'll just pick maybe a histogram that's right skewed. Okay, so we have a variable x there. You can tell that x is not normally distributed. X has some mean, and we know that for a right skewed distribution, that the mean gets pulled slightly off to the right. So it's not going to be right underneath the peak. That's where the mode would be and the median, but the mean gets pulled a little further out. So I'm going to just estimate it, and I'll say, suppose that is our population mean mu. Okay. This is the mean of x, our possible values of x, not our sample, not the mean of our sample means. Okay, so if this is our population mean, that's where mu would fall, and a right skewed distribution is just right of center. Then what we're going to say is realistically what we would do is, if mu is unknown, is we would start taking samples, and those would be of a given sample size, and we would calculate the resulting sample mean, x bar. So just like we did back with the dogs leaping distances, right? If we didn't know mu, we would take a sample and we would calculate a sample mean x bar. Okay, so because x bar is an unbiased estimator for mu, maybe I take a sample mean and I get this, this value, x bar. But that's just one of the possible sample means of that size, right? As we know from the dog's leaping distances, that for any given sample size, there are multiple individuals that could have been included, and so multiple different sample means that could have resulted. So maybe I do this again with a different sample, and maybe I get an x bar over here. So I'm going to call that x bar sub 2. Okay, and so what's going to happen is, again, all of these sample means are trying to estimate the true population mean mu. So I'm just going to start putting some in. Maybe I took another sample mean and got that value, and another one and got that value, and another one. So all of these are representing different possible sample means. Well, what's going to happen is they're going to be closely clustered around mu, but occasionally I'm going to miss, right? So occasionally I might get a whole bunch of bigger values and get a big sample mean. And occasionally I might get a bunch of smaller values and get a smaller sample mean. But most of them are going to be closely clustered about that mean. And if you can tell, what that does is it creates a normal distribution for the distribution of x bar. So whereas in black here, we have the distribution of x bar, which is approximately normal with mean mu and standard deviation sigma over the square root of n. Whereas the blue one, which was the distribution of the original variable x, not the x bars, not the sample means, but just the original data values, that one is distributed in some unknown way, right? It had a mean, it had a standard deviation, but it didn't look, I'm not going to use n because it wasn't normally distributed. Okay, so that's what the central limit theorem is telling us, and you can see it visually happening here. But it's telling us that even if x is not normally distributed, that the distribution of the possible sample means will be approximately normally distributed as long as our sample size is big enough. And again, big enough is usually about 30 or more. Sometimes it works when it's less than 30, depending on how far from normally distributed your original variable is. Okay, and then as a side note here, if your variable x is normally distributed to start with, so whereas this one was right skewed, let's say we started with one that was normally distributed, then x bar is also going to be normally distributed no matter what the sample size is. Okay. So this last page here is just going to be a summary that's going to walk us through what we just learned, okay? And what we're going to do here is we're going to still look at calculating probabilities of observing certain values, but we're going to look at probability of observing values of x as well as values of x bar. And so if you recall from the previous couple of sections, when we wanted to find probabilities related to observing a value of x, we'd use this basic z-score formula. So we said, well, z is equal to x minus mu over sigma. Okay. So for example, it says if we had the mean score on an aptitude test was 83 and the standard deviation was 7, what is the probability that a person scores a 98 or higher? So the idea here is this is trying to find a probability for X. This is one observed value. So a person. The extension we're going to make here is, well, what if I want to look at not just one person or one observed value, but I want to look at a mean? So this time we are going to standardize by still taking our variable of interest, subtracting its mean and dividing by its standard deviation. But we know that the mean of x bar is always equal to mu, and we know the standard deviation of x bar is always equal to sigma over the square root of n. So if we are trying to find probabilities related to observing a specific mean, so no longer one observed value but a mean, then we're going to use this to find the z-score. So we are told here a variable x with an unknown distribution has mean 45, so x is distributed, we don't know, with a mean of 45 and a standard deviation of 16. And we want to find the probability that the sample mean is between 43 and 46 for samples of size 35. Okay, so we want, this is not the distribution of x, this is the distribution of x bar. We know that the mean of x bar is always equal to the population mean, which was 45. And we know the standard deviation of x bar is always equal to sigma over the square root of n, where sigma was 16 and n was our sample size of 35. So we're going to get that standard deviation. 16 over the square root of 35 is 2.704. And so what we want to do is we want to find, we know that mu sub x bar is at 45, and we want to find the probability that the sample mean is between 43 and 46. For this distribution. And again, here's its mean, here's its standard deviation. And so the way to do that is we're still going to use normal CDF. And we can do that because of the central limit theorem. We know that x bar is going to be approximately normally distributed even though x wasn't, because we have a big enough sample size. So x bar is going to be normally distributed. Our lower value is 43. Our upper value is 46. Our mean is 45, just like the original variable had a mean of 45. But here's the place a lot of people are going to make a mistake, is the standard deviation is not 16. The standard deviation was 16 for x. We need to use the standard deviation of x bar, which was the 2.704 that we just found. Okay. And so we're going to second distribution, normal CDF from 43 to 46 with a mean of 45 and a standard deviation of 2.704. And we get 0.4145 if we round to 4 decimal places of the probability that the sample mean is between 43 and 46.